All right, so we are on page 36 now, and we're going to look at confidence intervals for the slope. So remember our example here. We randomly selected 25 U of I students from all U of I students, thousands of them, and got these 5 summary statistics, including this correlation coefficient right here between drinking and GPA. A negative correlation coefficient saying that the more you drink, the lower your GPA is, but this was only based off of 25 students, and we're wondering whether it would hold up if we sampled all 28,000 students. So we set up this probability model here, which is all 28,000 U of I students here, all U of I students, and each point represents one student. And for example, this student right here would be drinking a lot way down here and have a low GPA. Whereas this student up here would be drinking very little and have a high GPA. So the question is whether there's some negative trend here or not. So what we do then is, this is called the population scatter plot because it represents the entire population. So we'll say a probability model will make a population scatter plot. And then from that, we sample n equals 25 students out of here. So we randomly choose n equals 25 students and get this as our sample correlation coefficient there. And it's without replacement because we don't want to sample the same student twice. All right, now from here, we're going to calculate the sample slope for predicting GPA from drinks. Well, remember what the sample slope is. What the slope is R times the SDY over SDX. So in this case, R is negative 0.2 times the ratio of the standard deviations here. And Y is always what we're trying to predict. So it's going to be 0.5 over 5. Which is equal to negative 0.02. It's just and the units on that would be what? GPA points per drink. So for each extra drink that people consume per week, their GPA drops on the average 0.02 of a point. That's what that means. And so this right here is our slope. And we can call it, it's our sample slope. And we've been using Roman letters for that. So that would be B. All right? And now the relation, these look very similar, just off by 1/100th, by 1/10. And that's just because we multiplied by 1/10. That's just a coincidence here, because of the ratio of the standard deviations are 1/10. All right, now calculate the standard error of the slope, of the sample slope. Think of this as sampling error. Every time you take different points from here, you're going to get these different sample statistics and a different slope, right? So let's see if we can remember it and why it makes sense. Well, the numerator, 1 minus r squared times the standard deviation of y, is the spread around the regression line here, the population regression line here. Think of it as the more spread out these points are around the regression line, the more jitter there is, the bigger the sampling error. If all the points were on a line, there'd be no error, and we wouldn't get any sampling error, okay? And then divided by the square root of n. So this is like our usual standard error formulas, the standard deviation divided by root n. And the root n makes sense because the bigger the sample, the smaller the sampling error, the smaller the variation. If we just take a few points, like we could take this point, and that point, just by accident, we could get a positive correlation. Or this, and this, just by accident, we'd get a negative correlation. But it would be unlikely to take many points that all were radically different, that followed a radically different trend than the population itself. So obviously, the bigger the sample size, the more it reflects the population. All right? Now, this is a very easy mistake to make. You think, oh, we're done. But remember, here we are talking about a slope, and it has units, points per drink. And this is give or take. This is our wiggle room. This is a point estimate from our sample of the population, and we want to put a range on it. In the same units, well, we have y, it's a slope, so that's y over x. So obviously this is the wrong units, so that will remind us to put in a standard deviation of x, and that's our formula. All right, so now let's just do the calculation, and we have the square root of 1 minus negative 0.2 squared is 0.04 over the square root of 25, and then the ratio of the standard deviations is y over x, 0.5 over 5. And I did that, and I got 0.0196. All right, and that's the standard error, and now we're supposed to calculate a 95% confidence interval for beta, which is the true population slope from our sample slope, B. Okay, so now we'll do that, and let's draw a line here. And remember, the 95% confidence interval, we did this on the previous page, is going to be our sample slope right here, plus or minus a critical value of z that corresponds to 95% in the middle, times our standard error. So our sample slope is negative 0.02, and then we'll have plus or minus. Now we're going to have the critical value of z corresponding to 95%. So let's just remember what we're doing. On the previous page, we looked at that. Let's see where that is. It's right here. And if you look at this, this is what we're doing right here, the sample slope, plus or minus the critical value of z corresponding to whatever confidence interval you times the standard error. So this is, we want a 95% confidence interval, which corresponds to the area between the curve, on the curve between 2 and negative 2, or more accurately 1.96 and negative 1.96 if we wanted to be more precise. So the idea is that we see one particular sample, and 95% of the time will be in this range right here. Okay, so let's go back and write that. Okay, so here's our sample slope, plus or minus, we'll just round to 2 so we can do it more easily in our heads, times the standard error of the slope. And so we can do that in our heads. Why don't we just say approximate this? This is approximately equal to 0.02. So that gives us a range, and our lower limit would be negative 0.02 minus 2 times that minus 0.04, which would be negative 0.06. And our upper range would be negative 0.02 plus 0.04, so it would be 0.02. All right, so that's, we're 95% sure that if we sampled all 28,000 students or polled them all, that the slope would be in this range. Well, that range includes 0, right? So since this interval includes 0, we can't be confident that there's a negative correlation because it could range from negative to positive here. That's that's the interval we gave. In other words, the small negative slope in our sample could easily be due to sampling error. Now, notice that we only had a sample of 25. Since we have a small sample, n is less than 30, we should really be using a slightly different, standard error, and we should really be using the t-distribution instead of the z. So let's read y on the next page, and then do part t, and use this slightly different standard error, which is a little bit bigger, that's why I put the plus, and use the t curves instead of the z. All right, so let's read over here. Okay, so start here. All right, so for small samples, we're going to refine the distribution here. And we're going to first make two corrections. We're going to increase the standard error slightly by dividing, instead of dividing by the square root of n, we're going to divide by the square root of n minus 2. So remember what our other standard error formula looked like? It had the square root of n here, and now we have the square root of n minus 2. Now, why do we subtract? We do this when we're trying to estimate the standard error of the population. We don't know the standard deviation of the population. We're basing it on our sample. So we subtract because there are n minus 2 degrees of freedom. Remember when we were estimating the standard error of a sample average, and we divided by the square root of n minus 1, not the square root of n, all right? Because with 1 point, you have no way to estimate the standard error of the mean. You have no spread there to estimate it. So similarly, now, with a slope, you can't compute a slope with only 1 point, and with 2 points, you only get a single slope. 2 points determine a line. There would be no variation. So you need at least a sample size of 3 to estimate the spread around the line, to sensibly estimate the range of estimates of the slope. So to get an idea of how well the points fit a line, which tells you R, you need at least 3 points. All right? Now, you could use this standard error plus, the same standard error, with n minus 2 instead of n for the normal distribution like we did before. But when the standard error is estimated from data and not already known, you could do it when we don't know the standard deviation of the population, right? But we just know it of the sample. We could use this standard error plus. But when n is small enough for that to matter, well, then the normal distribution won't be appropriate then, and we'd have to use the t-distribution anyway. So for small n, let's say n less than 30, we're going to use a t-distribution, and we'll use this estimate for our standard error. Okay, so let's see what we're going to do here. So now we're going to do t-distributions for confidence intervals here, and we need this assumption number 4, which is normality of the errors. So if the sample size is too small for the central limit theorem to kick in, remember what the central limit theorem says. It says, maybe, first of all, what are we doing here? Okay, what is this normality of the errors? Remember what we're talking about with these assumptions here. Let me just quickly draw them again. So let's say we have this scatter plot here. And first of all, it has to be linear. That was our assumption number 1. And then we said that the spread, if we see this linear trend here, that there should be no clumping or pattern indicating non-independence of the errors. The errors have to be independent not only of each other, but of the x variable. And then we also said that the spread should be equal all along here. Like you shouldn't have them a fan-shaped pattern. Now, finally, we're saying this last, the fourth assumption, that we need normality. So what does that even mean? It means these errors should be normally distributed. Like, for example, all along this, for example, if you took a vertical strip, any vertical strip, we'd want a normal distribution of errors in here, meaning that more would be clumped close to the line and fewer would be out here, and it would follow like a little normal curve within every vertical strip like that. Now, why is that important? That is important because when we're trying to estimate the standard error of the slope, and if you don't, with just a small sample size, and you don't, you're going to get a bad, if the central limit theorem says that it doesn't really matter in the population if these are not normally distributed, as long as you have a big enough sample size, then the sampling distribution of the average will be normally distributed. But with a small sample size, we need to, that's not going to happen unless the data itself is normally distributed. So that's true for both the using the z and the t. But with a large enough sample size that you don't need that assumption of normality. But if you're going to have a small sample size, you do. All right, so that's where this fourth, right here, this fourth assumption comes in. That's normality of the errors. If the sample size is too small for the central limit theorem to kick in, then if the errors are normally distributed, that's assumption number 4, right here, we can use the t-distribution, just like we did for estimating means from small samples. So you should use the t when the sample size is small. I'm going to put an S for small. Now you can still use the t with large N. It's just not necessary. But most software programs do it anyway. So you'll see it being done all the time. It's just, it's easy if you click a button. Why not? But when we're teaching, when you're thinking about it, it really creates a cognitive burden. And if it's unnecessary, why do it? So yeah, if the machine's doing it, fine. But when we're trying to learn this, it's just very difficult to do it. It's much easier to think of the normal distribution because there's just one z-curve, one normal curve. Whereas with the t, there'd be a whole book of tables we'd have to look at. There's going to be a different curve for every sample size. All right, so now the errors around the regression line are approximately normally distributed. I'll put an N there. And finally, the standard deviations of the errors in the population are unknown, which is almost always the case. So this is almost always the case. And then, if all these conditions hold, you use the t. And I just remember it by the word snut, just because it's a burden. It's not a great. There's an overuse of the t in teaching, and it makes teaching hard. So this sounds like a dirty word to me, like slut or snut. It's an easy way to remember it. I mean, the t is an adorable distribution, and it's very cute, and I like it a lot. But it's just not a good way to teach people, and it's so unnecessary to teach them this way, because with large sample sizes, you'll see here in this illustration here, we'll talk about it in a minute, the t curves and the z curves with large n look almost the same. I mean, so we'll look at that in a minute. But first, let's finish here. So there are two differences between the simple normal z we showed and the t. The first is that we use bigger standard error plus. And here, let me just remind you what that is. So standard error plus of the slope is going to equal the standard error of the slope. But it's going to differ because here we divided by, this is bigger, and it's bigger than by a factor of the square root of n over n minus 2. Okay, so that's the first. We could do that for the z. It would give us an unbiased estimator of the standard error of the slope. It would be better to do, but we didn't bother to do that for the z, as we said, because by the time you use the z, you have a big enough sample size that this n over n minus 2 doesn't really matter. N over n, think about it, when n is really little, like 4, let's say 4 over 2, square root of 2, that would make quite a big difference here. But when n's 100, let's say, 100 over 98, well, that's just very close to 1 and is not going to affect things much. Now, we use the t-curves instead of the normal curves. The t-curves, that's a whole distribution of curves, are fatter in the tails. That's very important. Which means that for a given confidence interval, you have to go, they're wider. So let's look at these. And let's see. Now, the normal curve, right here, is the one that's tallest in the middle and skinniest in the tails. Remember, they all are 100%. They're all going to have an area of 100%, but it's distributed differently. So it's more bunched in the center. This is the normal. And skinnier in the tails. Whereas when you get to, now there's a whole series of curves, and k represents the number of degrees of freedom, n minus 2, for our slope. So when k is 1, that means n must be 3. And 3 minus 2 is 1. So a sample size of 3 would be this one right here. And this diverges the most from the normal curve. And you see how it's shorter in the middle. And more of the area is out in the tails. It's more spread out. It's fatter out here. And by the time, like here is k is equal to 20. So that means with a sample size of 22, you can see it's very close to the normal curve. It looks very close. All right. So now when we look at this, it says for a given confidence interval. So let's say for a given confidence interval, like as we said before on the normal curve, which is the tall one up here, this big one, between about 1.96 and negative 1.96, or 2 and negative 2, is 95%. But you can see with the t-curve shorter in the middle, 95%, you have to, that's not 95% of the area. You're going to have to go out further, which means that for a given confidence, you have a wider interval. All right. So now let's see what we want to do. We want to go back. Now that we understand that, we can go back and we can answer this question here, part D. So we can calculate the standard error plus of the slope. So let's do that. So it's going to be just like this one. The only difference being that instead of n, we'll have n minus 2. So let's do that. So we have the square root of 1 minus r squared over the square root of n minus 2 times the ratio of the sdy over sdx. So again, we have the square root of 1 minus, I'm just copying, 0.04, but instead of the square root of 25, what should we put in here? The square root of 23, and then we're dividing by the same thing, and multiplying by the same thing, the ratio of sdy over sdx. And when I did this, you see you're dividing by the smaller number here, you're going to get a bigger, that's why the plus is here, a bigger standard error. And what do we get? We get 0.0204. So now, that's the standard error plus. And now, how do we build our confidence intervals? This is where the t-distribution comes in. So we have a 95% confidence interval. And it's still our slope, our sample slope. But now, instead of plus or minus z, the critical value of z, we're going to do plus or minus the critical value of t, right? The critical value of t, corresponding to 95% in the middle. to find that critical value of t corresponding to 95% in the middle, we could use our online calculator or this t-table. Here's the relevant line from it, but let's first look to see where I got it from so you can see the picture. Okay, so let's go to our t-table back here. Excuse me, I just gotta find the t-table in the back of the book. Okay, so here's our normal table, and here's the one that's in the back of the book that's the t-table. So let's look at it here for a moment. Now, first off, as you see, there's these degrees of freedom, and for each degrees of freedom, there's a different curve that gets, as you get bigger, it gets more and more like the normal curve. So now we're going to look only at the line for our degrees of freedom, which is 23, which is way down at the bottom. So this is the relevant line, the one I copied. Now, which one of these do we want to use? Well, let's look up here, and what these headings tell us is the area just in one tail. The shaded area is shown along the top of the table. All right, so if it's just the area in one tail, this just happens to be the t-table that we're using here. Now, if it's the area in one tail, and we want 95% in the middle, this means 2.5% in one tail and 2.5% in the other tail. This would be a 95% confidence interval, right? And what's this? This is 1% in the right-hand tail. That would mean 1% in the left-hand tail, and this would be a 98% confidence interval. What would this be? This would be what? A half in each tail, which would leave 99% in the middle, etc. So we can just fill this in. This is 90%, 80%, and this would be 25% each tail, a 50% confidence interval. All right, so, and these are the critical values. So let's go back to where we were at. And now we can look at this table here to figure out the critical value of t. So between t, here's our 95% confidence interval. So this means between t is 2.07 and negative 2.07 is 95% of the area on the t-curve. This is for 23 degrees of freedom. So that's the critical value we want. And that, instead of the 2 or the 1.96, so we'll say 2.07. See, it's bigger. It's always going to be a bigger critical value. We have to go further out on the tail, on each tail's, further out on the curve to get the same 95% in the middle, because it's shorter in the middle, right, and wider in the tails. So we're going to say 2.07 times, and here we're going to put in our new standard error, plus. So I'll just write standard error plus, because we don't have room. And I did the calculation, and I got negative 0.062 when I subtracted 2.07 times that to 0.022. So this is a wider confidence interval than here. It would be even wider if I'd use 1.96 here. Okay, so let's write that down. So how does it compare to the one obtained using standard? The t confidence interval using the t distribution is always wider. All right, then using the z. Okay, so let's see what else we're going to do here. So we've done this. And now if we're on page 38, and actually we just finished, this is the same as the page we just did. I just thought we'd need more space, and we didn't. We fit it in very nicely on the other page, so no need to repeat it. So it's just the same, so we can cross that out. It's the same exact questions, etc. So now we're at the summary here, and just let's look at the summary. And so for large samples with independent, identically distributed errors, this is assumptions 2 and 3. So that's number 2 assumption and number 3 assumptions. To do this regression inference, we use this, right? We haven't used number 4 yet, normality. So this is all we need to do to compute a standard error for the slope right here. And the probability of the histogram, the probability histogram for the sample slope follows a normal curve, so we can use the normal curves to build confidence intervals. All right, and here's how we do that, using the critical values of z based on the normal curve that corresponds to whatever confidence level we're doing. I think we know that. Now we need to add for small samples. Here's where assumption number 4, normality, comes in, normality of the errors. It's needed in small sample sizes if we want to use the t-distribution. And then we need that assumption number 4, we need to look at that. And here, then when we use the t-distribution, we make a standard error plus, which is a little bigger, and then we use these t-curves. And the confidence interval has this form. Okay? So maybe we should note here, this is a good place, that the standard error for the slope, the standard error plus, is the same as the standard error for the slope. It's just multiplied by this factor of n over n minus 2. This is for simple regression. Okay? For simple regression only. When we add another variable, like add another predictor variable, for each one we add, we're going to have to subtract off another degree of freedom. So for example, if we had 2 slopes, it would be n minus 3, etc. So now our last thing we're going to do is going to look at hypothesis tests for the slope. All right. So sometimes instead of finding confidence intervals for the true population slope, we just want to get a p-value. We want to make a yes or no decision. For yes or no. Does the evidence we have from our sample allow? We want to decide to either reject the null, which is going to be that usually the population slope is 0, or not reject it. Okay? So we ask if the true population slope were 0, we assume the null. If it were 0, how probable would it be to get a randomly drawn sample to be as different from the slope of 0 as the one we found? So let's look at this. So basically the usual way we do it would say, okay, we assume that we have a sample slope minus our observed slope, which is our sample slope, minus the expected slope based on the null, which is 0. So we'll just leave that off, over the standard error for the slope. That would be our t statistic, and our z statistic would be the same thing. The observed sample slope minus our expected under the null of 0 over a standard error for the slope. So let's see what these look like. So remember, the slope is r, we call it, this is our sample slope, it's r sdy over sdx, and our standard error looks like this. And do you see how the standard deviations cross out and we're left without units. We're left with this t-statistic just in terms of r and n. That fully describes it. Same here. We're left with the z. With the z, we're left with the standard deviations cross out, and we're left with a sample, with a test statistic fully described by r and n. The doesn't matter what the standard deviations of y are. And that makes sense because if the correlation coefficient is 0, well, then the slope would be 0 too, right? For testing for it. The correlation coefficient is 0 if and only if the slope is 0. So basically, when we do a test statistic to test the null hypothesis that the slope is 0, we don't need this part of it. We just need to describe it in terms of r. And I simplified it here, so you see how really this here, I just simplified it, and instead of having, I just multiplied by the reciprocal here, and I get this nice statistic that's very easy to understand. And you can think of the numerator, this part right here, as describing the strength of our signal, of the model, the strength of the signal. You want a signal to noise ratio? This would describe the strength of the signal. The stronger R is, the stronger our signal is. And the more bigger our sample, the more evidence we have for that signal. So when you're going to get a bigger test statistic, remember bigger is further away, more extreme, we're going to get a bigger test statistic, the stronger our signal is. So the bigger n is and the bigger r is. And then in this part is a description of the strength of the errors. And we can do the same here. It's exactly the same thing. It's just here we subtract off 2 and here we don't. So this is our signal strength. And this part is our noise strength. And the ratio of those two is the test statistic we're using to determine if we basically have a signal or not. The strength of the errors is the noise. So we're just looking at, we did this earlier, right here on page 32. It's very similar to this. This is the r squared. The square of that statistic is featured in all regression analysis. So the square, if we squared this statistic, it's going to be, this one's going to be the F statistic, and this will be, at least for simple regression, this will be the chi-squared. And we'll look at that, that's in our next chapter, and that will be after the exam. But this is just a little preview. So then we obtain a p-value and look at how far out that is and assess whether to reject the null or not. So this is the important point here, is that our test statistic end up involving only R and N, not SD, R and N, not SD or DX. All right, so let's go back to our example here and do the same example that we did with confidence intervals using hypothesis test. So that's on page 42. And GPA versus drinks using the hypothesis test right here. We're on 42. All right. So this so far is a repeat. We're interested in finding out whether or not there's a negative slope in the regression equation for predicting drinking from GPA among all U of I undergrads. But we don't have the time and money to sample all 28,000 of them. So instead we take a random sample of 25 U of I students. And we've already done this, so we can say we found this slope, right, among the 25. Is it strong enough to conclude a negative slope in the population? So here's our sample statistics. We assume the 4 assumptions hold, and we have this, we get this sample regression equation. We didn't fill that part in, but you can see that we could solve for that because we could put in for GPA, the average GPA, which is 3, and then we get negative 0.02, and then here we could put in for drinks, the average drinks, and then we get negative 0.02, and then here we could put in for GPA, the average GPA, which is 3, and then we get negative 0.02, and then here we could put in for drinks, the average drinks, and then we get negative 0.02, and then here we could put in for GPA, the average GPA, which is 3, and then we get negative 0.02, and then here we could put in for drinks, the average drinks, which is 10, and then we just solve for that. And we can get the y-intercept. So that says 3 is equal to negative 0.2 plus what? Well, that's going to be 3.2. So that's our estimate of the intercept. All right, so we're going to argue by contradiction. Suppose there's no correlation, that the slope really is equal to 0 in the population. How likely would it be to get this big difference from that just by the luck of the draw? You formulate a null and an alternative hypothesis, and the null is the dull hypothesis that the slope of the population equals 0. Another way to write it would be beta 1 equals 0, the Greek letter. And the alternative is our observed difference is too large to be due to chance. It must reflect a real negative slope in the population. That's our, okay? That's our population parameter. And whereas the sample slope is equal to beta 1. All right? Now, set up a probability model under the null hypothesis. Imagine we chose 25 points at random without replacement from all those 28,000. The slope of the random scatter plot, the slope of the population scatter plot, is 0. So we'll just do our usual. So we have this thing, we have this population scatter plot. And this time it has all 28,000 students. Sometimes you don't know how many, and people just call it an imaginary population. But it has a ton of these 28,000, representing 1 point for every student in the whole population. And you've got your GPA here, and you've got your drinks here. And now the null is we assume that inside here, as opposed to with the confidence intervals, we didn't make that assumption. We assume what? That there is, the population slope here is completely flat, that beta 1 equals 0. And then we say, how likely is it to draw 25, to draw 25 n equals 25 points out of here? How likely is it to do that and get randomly chosen points and get, how likely is it, and we get a sample slope not equal to 0 but far away from 0, or is that far away or not? That's what we're trying to figure out. Okay? So we want to know how likely that is, and that's what our p-value is based on. Right? So that's the sample slope. We know that, of course, it's not going to be exactly 0. It would be unlikely to be exactly 0. But the bigger, the more points we sample, and the closer we'll get to that. Okay, so now what are we going to do now? So now let's do the hypothesis test here. So we saw, here's our t-statistic, which is going to follow a t-curve with n minus 2 degrees of freedom. And here's our z-statistic. And we're going to compute p-values from these two. All right, so let's jump down here, and we're going to use the distribution, either the normal distribution or the t-distribution. Let's approximate with the normal distribution first. Why don't we do it both ways? So here's our normal distribution, and we'll do the same thing with the t. Let's do this one first. So we're going to use our z-statistic, and here we'll do a t-statistic, all right? And here will be our t-curve. It's hard for me to draw it a little fatter in the tails, but that's our t-curve. Okay, so for the normal curve, we can start with that and just look at this, and what are we going to do? It's going to be negative 0.2 over the square root of 1 minus that squared, which is 0.04, times the square root of 25. And this this is not going to be given to you on the exam, so you'll have a lot of problems to help you remember this, and you have to think of it, some framework, so that this makes sense to you, and it will help you throughout the course if you do that. So this is not given to you. What's given to you is just the standard error of the slope, and that's on the front page of the exam. This is just what it's going to look like. You're only going to be given this. All right. So now these are simpler. All right, now the t, so let's do this. And I did it and I got negative 1.02. And now we're going to do this one. And this is the same exact r over 1 minus r squared. But now instead of the square root of n is the square root of n minus 2. And so, of course, this one is smaller. The t statistic is smaller in absolute value. All right, so we've got those two. And now, how are we going to, what we want to do now is, okay, we want to get our p-value. So we expect t of right here, but we want to find out how we want to get the area. How extreme is that? So what's the probability of getting this extreme t statistic or more extreme? Just by the luck of the draw when we'd expect 0. Okay, and we'll do the same. This is a z statistic, excuse me. This is a normal curve, z statistic. And here we're going to use a t. Well, which t? See, t's are kind of, it's hard to get an intuition for because each t curve is different. So this is the t curve with how many, degrees of freedom equal to n minus 2, and n is 25. So that's going to be 23 degrees of freedom. All right, and now we want to get between, say that's negative 1, 1, 2, 3, 2, negative 2, negative 3, and we want this. That's our t statistic, negative 0.98, and we want to know this right here. Now, we can't, you can look this one up on a table, but this, it's so hard to look at all the values for everything. We'd have a book, so it's much, much easier to use an online calculator. But before we do this, which do you think is going to be bigger? Do you think that the p-value is going to be bigger for t than it is for this one, or smaller? Remember, it's fatter in the tails. So fatter in the tails is going to mean a bigger p-value, which means you need more evidence to reject the null. You need to go out further to reject the null. All right, let's go look at our p-value calculator. And you won't have it, obviously, on the exam, so I'll just ask you to compare the p-values for the different ones. Like you could compute the p-value for z using the normal table, and then you just have to say if this is bigger or smaller than that. But let's just go online right now, and I can show you our p-value calculator so you can get used to looking at the curves here. So let's go to our PC, and let's look at the p-value calculator. Now you know how to use it for the normal distribution, right? The normal, it's just one normal curve for everything. So here we want to figure out, we have negative 1.02, and what do we want? We want the left-hand tail here, and now we want to compute the p-value, and it's 15.39%, and that's what it looks like. So write that down in your books, that the p is equal to 15.39%. That's pretty big. It agrees with what we got by confidence intervals, it's very plausible that we can't reject the null, that the correlation coefficient and the slope within the whole population is 0. But now let's compare it. So remember this. Now we said we'd expect to get a bigger, remember, fatter in the tails, a bigger p-value with a t. Now with the t, you have to put in the degrees of freedom. It's going to change. So we have 23 degrees of freedom, and our t statistic is negative 0.98. And now we want the left-hand tail the same way, and we're going to compute the p-value. And see, it's bigger, 16.86. You see that? 16.86. And it would be bigger even if we put the same exact, if we use the same standard error for both. So let's say we put in a negative 1.02. It's still, when we compute the p-value, it's still bigger. It's 15.92% instead of 15.39. And it would be dramatically different if this was a smaller sample size. Remember, with this, the z-curve doesn't change with different sample sizes. This one does. And now compute the p-value and see how it's 18.27. That's much bigger in the tail. And then, of course, if we make it really a huge number of degrees of freedom, we should get the same thing. And we do, 15.39. In the limit, the t and z curves are the same. So I think we can go back to our notes now. And I think let's just finish up here and write down what we just said. And so right here, here's our p-value. And here's our p-value here. So what's the conclusion? Can we reject the null? No, we're not far enough beyond a reasonable doubt to reject the null. We don't have strong enough evidence to say that would have been a very unlikely event. So we can, it's not less than 5%, certainly isn't less than 1% either, so we cannot reject the null.